This video will end our short introductory lecture on the isoparametric formulation. Remember what we've done so far. We mapped a generic rectangular element existing inside a larger two-dimensional mesh, existing in XY space, and mapped it to a standard square element existing in virtual ST space. We did this because we wanted to find a standardized way of deriving our stiffness matrix, our local stiffness matrix, which we can derive either in XY space or ST space. Our form in XY space is complicated by the fact that we need to derive the B matrix in a slightly different way depending on all the various orientations we could have a quadrilateral element existing in XY space, and that it's difficult to find the dA, or to find the area and to write the area that we're integrating over in terms of bounds of integration, which would be functions in terms of x and y. It's difficult to write a computer program or a computer algorithm to find the K matrix in this form. We can also find the same K matrix by integrating over ST space in our virtual coordinate systems S and T. This is the formulation I said we would end up with. I'm also not going to fill in the gaps of how we got here, but I can find the same K matrix by integrating over ds and dt, but now I know my bounds of integration are just going from -1 to 1. I showed you, and we found in the last video, how to find the B matrix inside this double integral. The B matrix formulation may have seemed complex, but it's easy for me to write an algorithm where I can find this B matrix for every single one of my quadrilateral elements in a set of standard instructions that I can easily write in a computer program. The only addition to this formulation is the determinant of my Jacobian. Finding the determinant of the Jacobian may seem difficult, and it is something that needs to be done for every single quadrilateral element that exists inside your mesh. The determinant of the Jacobian, in fact, only relies on the geometry of the element. It is, in fact, dA is equal to the Jacobian, the determinant of the Jacobian times ds dt. In an in-class exercise, we may go through finding the determinant of the Jacobian for a simple quadrilateral element. But for a computer program, we won't want to do that every single time. We want to find a standardized way of finding the determinant of the Jacobian. Without going through the details, I will present the final solution to that derivation here. For a particular element, with particular x locations for the 4 nodes, x1, x2, x3, x4, and y locations for the nodes, or x coordinates for the 4 nodes, y1, y2, y3, and y4, I can find the determinant, the Jacobian, which will turn out to be a polynomial in S and T by multiplying the row vector of our x coordinates to the column vector of the y coordinates by this matrix, which, notice, the matrix is dependent on S and T. When I am done evaluating this vector matrix multiplication, I will end up with a polynomial in terms of S and T. Note that I'm integrating over S and T, so after I perform all the integration, the dependence on S and T will drop out. All right, That's about as far as we're going to go in isoparametric formulation. Again, this is simply supposed to be an introduction to get you introduced to the concepts. If you want to learn more about isoparametric formulation, you can read information in your textbook.